Now we're going to move on and talk about fluids that are in motion. We have two types of fluid flow. We can have smooth type of fluid flow, in which case it's going to be called streamline or laminar flow. In that case, you can picture some streamlines right here as they go over something, say an airplane wing or something like that. You can see that the streamlines here, they're relatively smooth. That's a good thing. At a certain speed, then we start to get this type of flow called turbulent flow, in which case there's going to be some eddies behind an object. You can see right here the wing has been tilted up. It's going to depend on the speed of the object as well as kind of the shape of it, in which case we have to worry about the viscosity of the fluid, which is kind of related to friction. We're going to get these eddies, which in some terms is kind of good. However, if you're looking at efficient flow of an object, these eddies tend to slow you down. On the back of the trucks driving up and down 81, you see that some of them have a tapered end. What they're really trying to do is they're trying to change the shape of the truck to reduce this turbulent flow. For this class, we'll talk only about laminar flow, which is the smooth type of flow. The turbulent flow becomes quite messy, let's just say. What we can do is we can say, if we have a pipe and we have some mass going into that pipe, the mass going in must be equal to the mass coming out. Just kind of makes sense. This pipe is not going to swallow any of that mass. That lets us derive this fairly powerful equation that says the mass flowing in is equal to the mass flowing out. And we've done it over some unit time, so we're able to define it in terms of a velocity. This is called the equation of continuity, and it's actually a fairly simple concept, but it's very powerful in terms of the physics that can be done with it. If the density of the object doesn't change, then the equation of continuity simply says that the area multiplied by the velocity on one side of a pipe must be equal to the area multiplied by the velocity on the other side of the pipe. And if we had just a straight pipe with the same area on each side, all it really says is the velocity coming in must be equal to the velocity coming out. However, if the pipe is wider or smaller, then we can have differences in velocity, which I'm sure everyone here has played with a garden hose, and you constrict the area on one side of the garden hose, then what's going to happen is the water is going to flow out a lot faster and shoot a lot further. Where that comes from is essentially this equation of continuity, where we say the area times the velocity on one side must be equal to the area times the velocity on the other side, and a good time is had by all. A fluid can also change its height, and that leads us to another key concept called Bernoulli's equation, very important equation to know and be able to use. We can look at the work done, and we can say that the pressure plus the 1/2 density velocity squared plus the density times gravity times height must be equal to a constant. So all three of these must sum up to be a constant value, and we can have different values of velocity, height, and pressure, but all of those must sum up to be a constant. So I like to think of Bernoulli's equation as a conservation of energy, where here we're going to have essentially pressure energy. It's in pascals. Here we're going to have essentially a kinetic energy of the fluid, right? Looks a lot like 1/2 mass velocity squared. And here we're going to have the potential energy of the fluid. Because all these guys are constant, we can say that the pressure plus the 1/2 density velocity squared plus the density times gravity times height at one point, say this point over here, must be equal to the pressure plus the kinetic energy plus the potential energy over here on this side. And this is a very much like the conservation of energy for the mechanics stuff we looked at. This is a very powerful equation. We can use Bernoulli's principle to figure out the speed of water coming out of a spigot, where if we take a look at our setup right here, we have some water coming out of a spigot down here. What we can do is we can say at the very tippy top we're going to have essentially no velocity of the water. It's going to be pretty small, especially compared to the velocity that the water is going to come squirting out at. And we're going to have atmospheric pressure here. We're going to have atmospheric pressure here. And these are going to roughly be the same. This height differential is not very large. So what we can do is we can write Bernoulli's equation simply having two terms here and one term here. And we can rewrite this to figure out what the velocity is of that water coming out, and it's going to depend on essentially just the height differential, y2 minus y1. And you can kind of see as y2 approaches y1, as the water level gets lower and lower and lower, then the water is going to come out at slower and slower velocities. One application of Bernoulli's equation, which is kind of neat and interesting, is to look at how we have lift on an airplane wing. And mind you, this is just kind of a conceptual thing with an actual proof. If we look at these streamlines, which is going to be the path that an air parcel is going to take, it's going to travel a longer distance over here simply because of the shape of the wing. So what that means is we're going to have a much higher speed or a much higher velocity of a fluid on this side of the wing. Bernoulli's equation says that the pressure plus the 1/2 density velocity squared must be equal to a constant. So what that means is correspondingly on this side of the wing we're going to have a much lower pressure. On this side of the wing we're going to have a much lower velocity because the air parcel doesn't have to travel as far, so we're going to have a higher pressure. And objects tend to feel a force from regions of higher pressure to regions of lower pressure. That's how essentially having a small force on one side and a large force on the other side, but now we're talking about it in terms of pressure. Same type of thing applies to sailboats, where we have the wind. Its air is going to follow these little streamlines. We're going to have the wind going over the sails. It's going to be traveling much faster on this side of the sail than it's going to be traveling over here. So we can get a net force on the wind in that direction right there. The keel is going to help straighten it out, and we're going to get a resultant force that actually lets us sail into the wind, simply using Bernoulli's principle. And if you're really interested, you can look up something called tacking on the internet. Same type of thing applies to baseball using Bernoulli's principle. If we have a ball that's rotating with an angular velocity as such, we're going to have a high pressure over here. We're going to have lower velocities. Over here we're going to have a low pressure, and the ball is going to tend to curve in that direction simply because the ball is spinning. If it was not spinning, we wouldn't have this ability to curve the ball. Bernoulli's principle also has applications to the medical field. If we have someone that has a constricted artery, then what that means is the blood is going to have to flow much faster over here to get by that constriction, so we're going to have a high velocity. What that means is we're also going to have a low pressure on this side of the brain. On this side we're going to have a higher pressure, or at least normal pressure. What that means is we're going to be pulling blood straight back down and essentially away from the brain, and in general, taking blood away from the brain is not a good thing. Another application that you might see is something called a Venturi meter, and these are something that I used to use at NASA when we were flying on aircraft. We were interested in flow through our various tubing. Essentially what we did was we could measure the pressure at one point in the tube, and we know what the area is. We can then measure the pressure at some other point in the tube and know what the area is. And this difference in pressure, using Bernoulli's equation, pressure is equal to or pressure plus 1/2 density velocity squared, must be the same at both of these. We can figure out the velocity of the airflow through our tubes. Bernoulli's principle also helps explain the flow of smoke out of a chimney, and if you've ever laid awake at night wondering why animals in underground burrows are able to stay alive, they're breathing in oxygen and expelling CO2 just like we are, Bernoulli's principle can explain this for you. Typically these animals, I think that's a gopher, is going to have two different holes, and the wind speed can be different at these two holes. Here we have the wind a little bit higher up the hill. It's going faster, so we're going to have lower pressure, because we know that pressure and velocity are going to add up to more or less be a constant. Here we're going to have a lower velocity, so we're going to have a much higher pressure. So the air is going to flow from regions of higher pressure to regions of lower pressure, bringing fresh air to our gopher, who is now quite happy with us. It turns out that fluids also are going to have this property called viscosity. Essentially that's some type of internal friction, and I just want to mention it briefly. I'm not going to do a whole awful lot with this. If we consider having a stationary plate with a fluid on top of it, and we pull this plate with some force, then friction is inside of the fluid says that it's going to be moving fastest near the moving plate and slowest near the slowing plate, because then the slower at the stationary plate, because there is some internal friction. We can relate the force to this coefficient of viscosity, this little new guy right here, as well as the surface area and the velocity that you're pulling the plate and the length. All I really want you to essentially remember is that this new value right here, so higher values are going to mean larger friction, and you would see this in terms of everyday life. You're going to see this in terms of your oil weight. You're going to see SAE 30. That's going to have more viscosity, more internal friction than, say, SAE 10. So let's talk about the flow in a tube for a second. If we think about the rate of flow in a round tube, it's going to depend on, well, the viscosity of the fluid, how much internal friction it has, how much pressure you're applying to the tube. More pressure, faster flow. And of course the dimensions of the tube. Larger tube, you can get more flow out of it. It turns out that this volume flow rate is going to be proportional to the pressure difference between the two ends of the tube. It's going to be inversely proportional to the length of the tube and to the pressure difference. But most importantly, it's going to be proportional to the fourth power of the radius of the tube, and you see that in the next concept I'm going to talk about. So the application of this volume flow rate has medical implications. It has consequences for blood flow. If we look at an artery right here, and now we cut this radius in half of what it should be, kind of like what you see right here, the pressure has got to increase not by a factor of 2, but by a factor of r to the fourth in order to keep the same flow rate. We need the same flow rate because we need to get the same amount of oxygen to our brain and to our muscles. So the pressure has to increase by 2 to the fourth power, or 16. So this is when we start to see problems with the heart, because the heart just simply cannot work that hard for a long period of time, and blood pressure is going to go up as it tries to maintain the same flow rate. And lastly, my 3 summary slides for Chapter 10.